recording. All right, so we'll finish this relationship, right? Just like that. So we have this relationship established. And this is the UML version of what we had in our code. So arguably, this is something that you know, a useful representation of what we had. Of course, I could expand here as well, right? So I could say there is a private database ID which we never populate, which is an integer, I believe, right? And there are also a couple of these abstract methods declared, you know, inside the shape, which is I think we use like a quotes to show that the methods here are abstract. I think your textbook says that if you use this type of UML editor, then you can use quotation marks to indicate that the methods are abstract. So let me add something else to this diagram. If I had another class named drawing, right? Class which was named drawing, right? So drawing clearly is a collection of shapes. So I could use a method like draw, right? Draw everything, and it's a void method, doesn't return anything. But to indicate that drawing has a collection of shapes on this particular diagram, what I could do is just say, all right, this drawing is associated with the abstract shape. And I could also I really don't want this part. Okay, what I could do is that I could indicate, I think if you select the relationship, right click, you can go to properties of the relationship and basically label it with something that says, you know, 1 to many, to indicate the cardinality, to say that drawing, there's one drawing, but it can be, this is an asterisk on the other side. The drawing is really contains a collection of shapes, right? Because ultimately, if you look at my code, instead of doing all this work inside main method, what I could do, I could create a drawing class, right? Which would then manage, you know, instead of having this horrible hard coding, I could make it more intelligent and create a drawing class which will keep the drawing as you know, an array of some sort, as a private data attribute inside my drawing. And so essentially step away from main, keep main small, and have this work done in a separate class named drawing. But just to show you that this would be a useful or very possible situation where I would just say drawing is an association with shapes, just like this. And don't be surprised that although drawing knows only about shapes, but because shape class is abstract, that again will guarantee when the drawing talks to, at runtime, when drawing talks to the shapes, the calls are dispatched to the appropriate real classes such as circle and rectangle, and which also makes it possible to add a triangle to the picture very easily, right? So if tomorrow I wanted to also add triangle as a shape, I can very easily do that and just add it here, and I can keep going with all of this. So it's very expandable, right? I I can expand my design. It's very easy for me to add new shapes and so forth. And by the way, something else is that maybe there is a possibility that maybe I wanted to have different types of triangles. For instance, I could create a separate class for the right triangle or not a right triangle, and so I could further add other elements of inheritance to this class relationship diagram. That's really what class diagrams are, right? But interestingly, if I say a triangle, for example, there are different formulas to compute the area of triangle, right? There are different formulas that you can use to compute the area of triangle, and that could be the basis to create even more hierarchy of different triangles in the code. I'm not going to go into this discussion right now. I can perhaps write some code to demonstrate, but I'm just showing you that there are possibilities for even more further subclassing of triangles, as an example, in the future, and even more specializing triangles. So anyway, for example, the formula to compute, oops, again, I'm not, the formula to compute the perimeter of a triangle may be the same for all triangles. It's like A plus B plus C, but the formula to compute the area of triangle could be based on the base, the size of the base and the height of the triangle, or using that formula. I forgot the name of the of a formula where you basically take half of the perimeter and multiply it by sides subtracted from that half of the perimeter, and also would compute the shape. So there is a possibility to make that kind of diversification in the future. So anyway, but interestingly is that if I create all these objects and populate array of shapes inside of my drawing, then when at runtime, when I make calls to these objects, the calls will be properly dispatched to the right object, and so I can take full advantage of this polymorphic behavior which is available. By the way, what we saw here when we said, shape get area, this is a version of uniform interface into our shapes, and that universality of the interface that each particular shape provides and promises to implement in our code is called polymorphic behavior. The idea of dispatching these calls to individual methods defined by each of our classes in this inheritance relationship that we have is called polymorphic behavior, or simply polymorphism. Is that you get one interface, but it takes many shapes, many ways to conduct those operations at runtime, and this is called polymorphism. So again, kind of fancy buzzwords, but the most important thing is that if you should ask yourself, do I feel comfortable with the sample that we have right now? Because this sample absolutely 100% demonstrates polymorphism in action. This is polymorphism. So what are the steps to achieve polymorphic behavior in our application? First of all, find classes that are relevant and which have common pieces. Then everything in common goes to the top of the hierarchy, which is an example of a shape. And then real subclasses are derived from that top level common thing. And then you can use collections of those base types, such as shape, right here. So drawing, if the drawing class did exist, then it could have an array of shapes, and that's what this diagram indicates. That's the UML version of showing you that, hey, there's a placeholder for like a collection of shapes. Okay? So there, this collection of shapes provides you the access to this polymorphic behavior. So again, quick review of achieving this polymorphic behavior. Create class inheritance. Use superclasses to dispatch method calls to appropriate subclasses, and that's the dynamic polymorphism, a runtime polymorphism provided automatically by the programming language. We didn't have to do any coding. We just, simply because we said shape class is abstract, then we said rectangle extends shape, and make sure that you provide get perimeter and get area. Same work done inside the circle, right? Circle does extend shape, provides get perimeter and get area. And this is it. And so then when you start using it, polymorphic behavior is instantly available. The right methods are invoked, and everything just works. So there is a little bit of extra work with organizing our classes into this inheritance relationship, but once we have it, it becomes kind of useful because, like I said, if I decided to add a triangle, I just create new class, extends shape, and start coding. Everything is in place, and the main method also will continue to operate. Where's my